Okay, good afternoon, everybody. So, in the last lecture, we have learned now that how we can use unpolarized neutron beam to get the information about the spin-spin correlation, means about this static magnetic structure, what kind of information we can get it. And by using this full Prof program, we have learned that by using this representation analysis, how one can solve the magnetic structure and can get the information about the magnetic ordering. But as you know that neutron has a spin, so one can in principle get this polarized neutron beams. So what are the advantages if you want to work with the polarized neutrons? So the additional information you can get using polarized neutrons is, first of all, as you know, neutron scatters by the unpaired moment in your sample. So by doing polarized neutron diffraction study, you can get an idea about spin density distribution. So you can get idea that how this spin density is distributed in your sample. You can get the idea, suppose you have ferromagnetic structure and the moment size is very small. So you can determine those kind of magnetic structure. And when you do inelastic kind of neutron scattering experiment, which will be covered in this next sessions, then if you use polarized neutrons, then you can separate the magnetic contribution from this nuclear contribution. So it means you can separate this magnon in your excitation spectra from the phonon. Phonon and magnon separation. So these are the major things which you can do by using polarized neutrons. So in this lecture, we will first learn that how one can produce this polarized neutron beams. So I will start with the double differential scattering cross section for the magnetic scattering. And I introduced in the last lecture how we define the polarization of the beam is, we define polarization of the beam as P equal to n plus minus n minus so this is how we define polarization of the neutron beam. So n plus is number of the spins up spin, n down is number of spin down neutrons, and n plus, sorry, this is n plus n minus. So this is total number of spins. So this is how n plus is. What we are assuming right now is that we are applying this magnetic field along the z direction. So we are seeing this neutron spin polarization along the z direction. So number of up spins, number of down spins, and n is equal to n plus n minus total number of spins. This is how we define the polarization of the neutron beam. Now let's start from this basics that, so let me write down the double differential scattering cross section. So let me write down the double differential scattering cross section where the neutron changes its wave vector ki to kf. Neutron changes its spin from Si to Sf after scattering, and the state of the scattering system changes from initial state to the final state. And now let me write down here the double differential scattering cross section, which is written as d square sigma over d omega final def. And in this process also energy of the neutron changes from ei to ef. So these are the scattering variables we have, and this double differential scattering cross section is given by this equal to, with the condition that Si to Sf. So this is given by Kf over, let me erase it, and so double differential scattering cross section d square sigma over d of omega f and d of ef, where neutron changes its spin from Si to Sf, and this is given by Kf over Ki sum over I and F, initial and final state. This is the weightage factor, statistical weight for the initial state, Pi, or the probability. And then what we have is this matrix element, F is the final state, and this is sum over the site UL, sum over the site L, exponential iota Q dot RL, U of L S I S F, and this is with the initial state. So this is the differential scattering cross section, and what we have here is UL SI SF. It is nothing but atomic scattering. This is atomic scattering amplitude for site L, describing a process in which neutron changes its spin changes from Si to Sf. So let's write down this expression for this ULSF. So this U is equal to SF final spin. B of L is a nuclear coherent scattering amplitude for the site L minus PL is the scattering amplitude, magnetic scattering amplitude. SI perf is telling that we are sensitive only to the component of the moment which is transfers to Q, and this dot sigma, where sigma is Pauli spin matrix and SI. So this is the factor BL. Here is nuclear coherent scattering amplitude. Nuclear coherent and P is magnetic scattering amplitude for the site L. Now, what I have neglected here is nuclear spin. So I am neglecting here this scattering from the nuclear spin. So let me write. I am neglecting here nuclear spin. So I am neglecting this scattering from the nuclear spin. And S perp here is, as you know, is Q is the scattering vector. So it's the unit vector along the scattering vector direction crossed S. So what it makes sure is that when we are doing the magnetic scattering, we are only sensitive to the component of the moment which are transfers to Q. So I can write this S perp as so let me write it. So another way I can write this so I can write here this S perp equal to S minus so you can see if S and Q are parallel, then this S perp, then this vector becomes S and this is unit vector. So this is also S. So this S perp becomes 0. So when your moment is aligned along the Q, you will not get any magnetic scattering. And sigma here are the Pauli spin matrix. So I can write them as, so sigma x is 0, 1, 1, 0. Sigma y is 0 minus iota, iota 0, and sigma z is 1, 0, 0 minus 1. Now let's assume that z axis is the direction of neutron polarization. So let's assume now that initial neutron polarization is along the z direction. Means we are applying this magnetic field along the z direction. So initial so now by using these properties of Pauli spin operator, I can write this u in the four terms. So what I can write it, you can do this mathematics by yourself, and I'm writing the end result u plus plus. Means my up spin goes to up spin after the scattering. So I have the neutron with this spin up, and after the scattering, it goes to this, it remains as a spin up. So it means no spin flip. This process, you can write it as B minus P as per Z. Similarly, you can write minus minus means you have a neutron beam with the spin down, and after scattering also it remains spin down. So this can be written as B plus P as per of Z. So this two processes describes this non spin flip scattering. So means neutrons spin remains same after the scattering. Another two elements are plus minus, means you have the up spin beam and after it becomes down spin. So we are describing the spin flip process, and this can be written as minus P. Here P is the magnetic scattering amplitude, and this can be written as, and we are assuming that initial neutron polarization is along the z direction. Plus iota s. So this s per factor becomes like this, and the fourth is you have the spin down, and after scattering it becomes spin plus. So this is also the spin flip process, and this can be written as this just comes by putting this Pauli spin operator and doing some mathematics. So these two process where the spin of this initial neutron gets flipped. So these are called spin flip process. Now let's take a system and let's assume that Q means your scattering vector is in the direction of polarization, neutron initial polarization. So suppose now if I start with the case 1, Suppose Q means your scattering vector. Suppose if it is parallel to the neutron polarization. In this case, and suppose this is parallel to z-axis, let's assume this. So in this case, as you know, this component S perp z is going to be 0 because you cannot sense a component of this S along the Q. So in this case, what you get is this, all this magnetic scattering, which is written here. So all magnetic scattering goes to the spin flip side. So in this case, please keep this always in your mind. If your scattering vector is parallel to P, means initial neutron polarization, then all magnetic scattering goes to spin flip, because you cannot sense the moment component along the Q. So it means this S perp Z, they become 0. So in this case, please always keep in your mind that when Q is parallel to P, then all magnetic scattering goes to spin flip channel. So all magnetic scattering please understand, because if the Q is parallel to P and let's assume it is Z axis, then this part which is representing like this magnetic scattering contribution, this becomes 0. So what you are left with is only nuclear scattering. So it means if your scattering vector Q is parallel to P, then all magnetic scattering goes to the spin flip channel. Please keep always this in the back of your mind when you are doing the experiments with the polarized neutron. Now let us consider case number 2. So case number 2 is case 2. Case 2 is suppose Q is perpendicular to the neutron beam polarization and this S vector is parallel to the P naught and is parallel to the Z axis. Suppose you are doing an experiment in the horizontal scattering geometry, and in this case, if you are doing an experiment in the horizontal scattering geometry, then your Q vector will be in the horizontal scattering plane. And now suppose, and let me assume that this horizontal scattering plane is XY. So this is, let's say, suppose my horizontal scattering plane, and Z axis is suppose out of the board. So this is Z axis. In this case, what you see is that all magnetic scattering goes to non-spin flip. So if you have Q which is transverse to P naught, means you have the horizontal scattering geometry, your initial neutron polarization is along the Z direction, then what you can see is that all magnetic scattering goes to this non-spin flip channel. So this is the advantage when you want to use the polarized neutron to investigate your material. So advantage is that by using this proper combination, one can separate the spin flip and non-spin flip processes, and one can separate this nuclear and magnetic scattering. So I believe you understand this part number 2. Suppose Q is in the horizontal scattering plane, polarization of your incident neutron beam is vertical, and suppose this is the direction of Z, and suppose that is the direction of S also. In this case, all your magnetic scattering will go to non-spin flip. So so by using then this polarized neutron beam, one can separate spin flip means and non-spin flip processes. It means one can separate this nuclear and magnetic scattering. So suppose you have the sample, and if you polarize its spin along the z direction, and you are working in the horizontal scattering geometry, and your initial polarization of the neutron beam is along the z direction, then all your magnetic scattering will go to non-spin flip. Please keep this in the mind. Now, let's try to get this double differential scattering cross section under the condition when Ki equal to Kf, means you are dealing with the elastic scattering, and so then I can write this differential scattering cross section separately for the spin flip and non-spin flip processes. So I can write plus goes to plus, means your up spin goes to up spin after scattering and down spin goes to down spin. This I can write it as sum over mn exponential iota q is my scattering vector, and these are the position of the atom, magnetic atoms, into b of m, b of n star, plus minus. Plus is for the case where you are coming with this up spin beam and it remains up after the scattering, means plus plus, no spin flip, and minus is the case for this you come with this down spin neutron beam and after scattering also this is coming down, so this sign is for the lower one. And what we have here is, so then plus minus this b of m. So p is here the coherent scattering length, and s n perp z. So this is complex conjugate plus bn p of m. P is the magnetic scattering length, s of m perp z plus third term pm pn Sm per Z, Sn per Z. So this is the differential scattering cross section under the elastic condition. This you can get it if you put this u plus plus and u minus minus in your double differential scattering cross section and make it E equal to EF. So this is the expression you get it for the known spin flip process. So this process describes the remaining two spin flip processes. Also I can write it at, so let me write remaining two this spin flip processes, that is plus goes to minus, means you start with this up spin neutron beam and it goes to down spin, means there is a spin flip, and the another process is minus plus. So this is given by sum over m and exponential iota q is again the scattering vector, which is kf minus ki rm minus rn into pm magnetic scattering length pn, and then you have bracket something which I am writing it here. The quantity in the bracket is S m per x Sn per x plus S m per y Sn per y minus iota S of m per cross S of n per star, where the star is the complex conjugate, and one can easily see it here that the S per Z component, so let me write it down again. So what we see here with this two expression is that this contribute to the non spin flip process, and S per x, this contributes to the spin flip process. You can see it here. So this is the spin flip process. So this contributes to the spin flip process. Well, to make it clear, and this thing here represent the part which is supposed to come in this bracket. Now let's consider the special case, and let's consider a unit cell with a single atom. So Now let me consider unit cell with a single atom, means I have only one type of atom, and let me assume that I am working in the horizontal scattering geometry and my scattering vector q is perpendicular to the initial neutron polarization vector which is parallel to the z direction. So your initial neutron beam is along the z direction, vertical direction, and you are working in the horizontal scattering plane. And this also, let me assume that this S is parallel to the P naught is parallel to the Z axis. So your S is along the Z axis. So one can easily see in this case is S equal to S perp equal to 0, 0, S perp of Z. S perp of X and this I am assuming 0. So then I can write the differential scattering cross section for the non-spin flip process. So it means I have some sample, I have some single crystal in which my magnetization or S is aligned along the Z direction. Let's suppose I have magnetized this crystal and my initial neutron polarization it means is along the Z direction and I am working with the horizontal scattering plane. So in these cases, I can write my differential scattering cross section for the non-split flip process which I wrote. So this expression becomes plus plus minus minus. It means there is a non-spin flip scattering. So in this case, you can easily write, I can write it as B square, means I have written in the previous expression Bm and B n star plus minus 2 B P S plus P square S square. This becomes B plus minus P S. So suppose now if I have some special crystal for which this coherent neutron nucleus scattering length is equal to PS, means magnetic scattering length. If I have a crystal for which B equal to PS, then you can easily see that this d sigma over d omega has finite value for the process plus plus B plus, if it is equal, it becomes 2PS or 2B. And for the process d sigma over d omega, this is 0. So this provides me a way to produce polarized neutron beam. So I need a crystal for which nuclear scattering length and magnetic scattering length are equal. And suppose this is a crystal, I work in a condition that my Q is perpendicular to the P naught initial neutron polarization. In those cases, I can easily get this polarized neutron beam by using these crystals. And what are those crystals? So I will write the name of these crystals which can be used to produce this polarized neutron beam. So one of this is Cu2MnAl, Husler alloy, and this condition B equal to Ps is satisfied for 111 reflection of this Husler alloy, which is given, which has a D value of 3.43 angstrom. So one can use this Husler alloy crystal to produce the polarized neutron beam. The another material which can be used to produce polarized neutron beam is cobalt alloy, which is cobalt 0.92, and iron. And for the 2000 reflection of this single crystal, which is given by D equal to 1.76 angstrom, your nuclear coherent scattering length becomes equal to PS, and this provides a ideal opportunity to get the polarized neutron beams. Well, there are other ways to produce the polarized neutron beam. So other way to produce the polarized neutron beam is using polarizing filters. Means by the preferential absorption by helium-3 nucleus. So you keep this nuclear helium-3 nucleus spins aligned by optical pumping. And the other method is by polarizing mirrors and super mirrors. I think there will be class in coming lecture about this. Polarizing mirrors. And the third, which I have discussed, is by polarizing monochromators. So these are the ways by which you can produce the polarized neutron beam. But please remember this one thumb rule when you are doing polarized neutron scattering. If your P is parallel to the scattering vector, means initial neutron polarization is parallel to the scattering vector, then all magnetic scattering goes to the spin flip channel. Please keep this in the back of your mind. Now, let's quickly understand what we do with this polarized neutron scattering, or what we measure in a polarized neutron scattering experiment. So what we have at Dhruva is the polarized neutron spectrometer. So this is the polarized neutron spectrometer. So here you can see this, we have the incident neutron beam which is unpolarized, and we used this 111 reflection of the Husler alloy Cu2MnAl to produce the polarized neutron, and this is guide field to keep this so that neutron beam do not lose its polarization, and this neutron beam then interacts with the sample, and then again we have analyzer to check the polarization of the neutron beam. And this is the detector. So what kind of information one can get by the polarized neutron spectrometer is that, so generally suppose you have ferromagnet and suppose magnetic intensity is very, very weak in comparison to the nuclear intensity. So what you do in those cases is you measure the flipping ratio by up and down process. So what you measure is the flipping ratio so you measure the flipping ratio which is given by Fn plus Fm and Fn minus Fm. And suppose now, and let me define gamma as Fm divided by Fn. So I can write it as 1 plus gamma upon 1 minus gamma. Now suppose you have Fm which is very, very small in comparison to Fn. Then when you do this unpolarized neutron diffraction experiment, what you will see is that you will try to see this gamma square. But by doing this polarized neutron scattering experiment, by measuring this flipping ratio for a couple of reflections, you can even find out about this small moment which is present in your sample. So this is the one example. Another thing which you can do with this polarized neutron is that between the PPT, I think I lost the PPT. So that another process you can do it, you can use this polarized neutron spectrometer in the direct geometry means you can check how this neutron beam when it passes through your sample gets depolarized. So this allows you to check whether there is some sort of ferromagnetic correlation at the length scale of say 100 to 1000 angstrom, and then by checking how much neutron beam is depolarized by passing your sample, you can get idea about this ferromagnetic domains. You can calculate this domain size. So let me give you a small example. So in the example which we were discussing, this NDFE MNO3, in which there is a spin reorientation where your spin changes, magnetic structure changes from the GY type antiferromagnet to GZ type antiferromagnet when you come from 90K to 4K. And in this process, what you develop is a ferromagnetic component, and you can see it by doing this neutron depolarization measurement. It means by just seeing that how much your neutron beam gets depolarized after passing your sample, we see there is a depolarization of neutron beam, and it gives an idea that when your spin is reorienting from GY to GZ orientation, then there is some net ferromagnetic component which is developed in the sample. So this experiment helps you to find out if you have ferromagnetic correlation at mesoscopic length scale. With this, I would like to end this today's lecture, and I will take one lecture at the last about this magnetic inelastic neutron scattering, which is used to measure this spin excitations, means magnons in your magnetically ordered state. This I will take after the lecture from the phone on. Dr. Basu will brief you. But at this time, if you have some questions regarding this part or the full prof part, you can ask. I believe this data file will be uploaded very soon or might have already uploaded. It will be uploaded on Anuvidya probably today or tomorrow, and then you can exercise with the data file. And when I come after a break, you can ask some questions if you have about this full proof data analysis in this example files which will be given, which will be loaded on this Anuvidya portal. I will load the tutorial, I think in a day or two, and you have to submit this tutorial before I come for the next lecture, which will be, I think, after 2 weeks or so, 2 or 3 weeks. Next month. January. So it will be in January. That's what Dr. Basu is telling me. So I think you can ask the questions now. There is no question, then I think Dr. Basu will like to brief you for your next series of these lectures.
Good afternoon, friends. So I'm back again to brief you about the next module. Theoretically, the module on magnetic neutron scattering ends here, but only one small part, not small in principle, but a small thing regarding inelastic magnetic neutron scattering has not been taken up. So the next module will be taken by Professor S.L. Chaplot, who is an expert on inelastic neutron scattering. So this is something which is very interesting, and unlike any other microscopic techniques you have done, this will discuss how you can measure dynamics using neutrons, because neutron, as I told you in the initial lectures, that neutron has an energy of milli-electron volt, which is comparable with the energy associated with the dynamics in solids. So Dr. Chaplot, Professor Chaplot will tell you about inelastic neutron scattering. So that he will brief you about phonons. He will talk to you about quasi-elastic neutron scattering, which can be used to measure diffusion. And possibly after that, Dr. Anil Jain will come back, and the magnetic counterpart of phonons are magnons. So he will talk about magnons. Now, let me tell you, please note it. I will also post it at Anuvidya. The next talk will be on 4th of December. 4th of December is a Friday, I think. It's a Friday because next week we have a busy schedule. So we are not able to go with the usual schedule. So we'll start with 4th of December. Following that, it will be again Monday, Wednesday, Friday mode for rest of the month. And next module we will try to end, at least next month, courses will try to end by 23rd of December. There will be a 1 week holiday for all of us, lecturers as well as the students. Then we'll start again in January 2021. So please note that it will be 4th of December, Friday, 3 p.m., the next lecture. And I must tell you that I have received the sheets for the second assignment for quite a few of you, but not everyone who had given the assignment 1. If you want credit, you need to submit the assignments within the scheduled period. Otherwise, we are happy to tell you about all these things, but then credits will not be there. So I'll tell you, please remember that if you want credits, you must submit your assignments. So today's talk ends here. See you on 4th. Okay, there are awards. Also, I can tell you that this on 2nd we don't have a talk lecture because HBNI will have its awards ceremony on that day, when we give the best thesis award and the best thesis awards and best MTech project awards to students. And because of that, we can't hold the lecture on 2nd. The next lecture is on 4th. So that's it. Goodbye. बंद कर दो.